Hello everyone, and welcome to today's presentation. I am Dr. S.K. Singh, and I am pleased to be here with you. Today, we will be discussing purified water storage and distribution. Over the course of this presentation, we will explore key aspects of how purified water is stored, managed, and distributed effectively. I look forward to sharing insights and engaging with you all. Let's get started. Water storage and distribution systems are crucial parts of the overall system. Usually, purified water is stored in a vessel for subsequent use. It's important to recognize that the storage and distribution system isn't just a passive component. It needs to be properly designed to ensure safety and quality. A well-designed system helps prevent microbial proliferation and recontamination of the water, whether it's purified water, bacteriostatic filtered water, or water for injection after it has been treated. This is vital for maintaining the integrity of the water throughout its journey in the system. Additionally, implementing both online and offline monitoring is essential. These monitoring methods help us verify that the water continues to meet the required specifications at all times, ensuring safety and compliance. Overall, the storage and distribution system supports the entire water quality assurance process, so careful design and continuous monitoring are key to maintaining high standards. Now, let's take a closer look at the key components involved in our water purification process. First, we have the hydrophobic air filter and burst disc, which play a crucial role in ensuring that gases and potential pressure buildups are safely managed. Moving along, the ozone generator is essential for sterilizing and disinfecting the water, providing a powerful oxidation process to eliminate contaminants. Next is the heat exchanger, which helps us control the water temperature efficiently during treatment. The feed water, which can come from DI or RO systems, feeds into the process, ensuring we're starting with high-quality raw water. To further refine the water, we include an optional inline filter with a 0.2 micron pore size, capturing even the tiniest particles. A hygienic pump then moves the water through the system, maintaining cleanliness and preventing contamination. The outlets are designed to safely release air brakes to drain, helping maintain system integrity. Additionally, we have a cartridge filter at 1 micron, which provides an extra layer of filtration for removing fine particles. The spray ball ensures proper water distribution and agitation during cleaning cycles. It's important to remember that water must be kept circulating continuously to prevent stagnation and ensure consistent quality. Finally, the water storage and distribution systems work hand in hand with the purification plant, ensuring that clean, high-quality water is reliably delivered to the end-user points and that the purification equipment operates at its best. Altogether, each of these components plays a vital role in maintaining the integrity and efficiency of our water treatment process, ensuring we deliver safe, reliable water for your needs. Let's talk about jointing first. It's essential that our joints are smooth to ensure a secure and reliable connection. We need to control the process carefully, which includes welder qualification, proper setup, and conducting work session test pieces. Keeping detailed logs and visual inspection reports helps us maintain quality and traceability throughout. Moving on to unions and valves, their sanitary design is crucial. Specifically, avoiding threads helps prevent bacterial buildup and makes cleaning easier. When selecting materials, we typically use options like SS316L stainless steel, polypropylene, or PVDF. The key here is compatibility. These materials must withstand the specific temperature ranges, chemicals, and operational conditions they'll face. This also includes considerations for resting and sanitization procedures. A critical point is preventing leaching. We want materials that are non-leaching during operation and sanitization to avoid contaminating the product. Corrosion resistance is another major factor. For instance, SS316L is excellent because it withstands cleaning and passivation processes, which help maintain its integrity over time. Internal finishing should be smooth, especially for water storage and distribution systems, to prevent buildup and facilitate cleaning. When it comes to contact materials, those that touch the WPU, they must be appropriate for their function. This includes pipework, valves, fittings, seals, diaphragms, and instruments. Ensuring the right material choice here is vital for safety, durability, and compliance. Overall, every component and material must work together seamlessly to support the integrity and safety of our systems. Now, let's talk about the systems we have in place to control the proliferation of microbes. It's essential to understand that effective sanitation and sterilization techniques are at the core of maintaining a safe and compliant environment. One key aspect is considering microbial control right from the design stage, which means choosing suitable materials of construction that minimize contamination risks. This proactive approach helps set a strong foundation for effective cleaning and sterilization processes later on. Speaking of procedures, it's vital that we follow validated methods for cleaning and sterilization. Validation ensures these procedures are reliable and effective, providing confidence that microbial levels are kept in check. Another important point is the need for special precautions when water isn't kept above 65 degrees Celsius. At lower temperatures, microbes can survive more easily, so we have to implement additional measures to ensure proper microbial control under these conditions. Finally, system sanitization and bioburden control are ongoing priorities. Regular cleaning, validation, and monitoring help us maintain low microbial levels, safeguarding both product quality and patient safety. All of these measures connect back to our overall goal: creating a safe, compliant environment through effective microbial control systems. When we consider design and size, these aspects are absolutely crucial for ensuring a reliable and efficient process. First, let's talk about capacity. It's important to have the right buffer capacity, meaning the ability to generate and use materials without interruption. Operating continuously is key here, as frequent on and off cycles can cause inefficiencies, so designing for steady operation helps maintain optimal performance. Having sufficient buffer capacity also provides a short-term reserve in case of unexpected failures or disruptions, which adds an extra layer of safety and reliability. Now, when we look at contamination control, there are several design considerations to keep in mind. For example, headspace, the space above the material, should be kept wet using spray balls or distributor devices. This helps prevent contamination and buildup. Nozzle design is also critical. They should be designed to avoid dead zones where material might stagnate or contaminate. Vent filters play a role too. They need to be chosen carefully, tested regularly, and used with heat to prevent microbial contamination from entering the system. Pressure relief valves and burst discs should be of sanitary design, meaning they are constructed to prevent contamination and facilitate cleaning. Lastly, storage vessel requirements are equally important. They must be appropriately sized and designed to ensure safety, cleanliness, and compatibility with the process. All these elements, capacity, contamination control, and proper vessel design, are interconnected and vital for maintaining the integrity and efficiency of the entire system, aligning with our overall goal of robust and safe production. Let's take a closer look at the storage vessel. When considering a storage vessel, it's important to think about the key components that ensure it functions effectively and safely. These components include the vessel material, which needs to be compatible with the stored substance, and the design features that prevent leaks or failures. Additionally, we need to consider considerations like pressure ratings, temperature controls, and the vessel's capacity to handle the storage requirements. These factors are crucial because they directly impact safety, efficiency, and the overall integrity of the storage system. Connecting this to the broader theme of our presentation, a well-designed storage vessel is fundamental to maintaining process safety and operational stability. It's not just about holding a substance, it's about doing so in a way that aligns with safety standards and process needs. Let's talk about heat exchangers and how to prevent contamination. It's crucial that they are not a source of contamination themselves. That's why we prefer configurations like double tube plate, double plate and frame, or tube and shell. These designs help minimize contamination risks. Additionally, arranging the heat exchangers in continually circulating loops or subloops is essential. This setup prevents stagnant water, which can be a breeding ground for microbes. When cooling is required, it should be done for the shortest possible periods to limit potential contamination. Temperature control is vital too. Maintaining precise temperatures helps inhibit microbial growth. Using continuous circulating loops further supports this goal by ensuring water is always moving, which reduces stagnation. We also need to control the proliferation of contaminants. One way to do this is by avoiding filters in the loops or at user points, which can sometimes become sites for microbial buildup if not maintained properly. Circulation pumps should be designed with sanitary standards in mind. Think of features that prevent stagnation and are easy to clean. Having standby pumps is also a good practice. They ensure there's no stagnant water when the system switches over or during maintenance. When it comes to water distribution pipework, general considerations include ensuring the pipework is designed to promote flow and minimize dead zones where water might stagnate. Proper pipework layout and maintenance are key to maintaining water quality throughout the system. Let's start with the concept of minimized deadlegs, which is crucial in maintaining water quality. Using NMT3D systems helps reduce these stagnant areas where bacteria can thrive. Moving on, it's important to have pressure gauges separated by membranes, ensuring accurate readings without interference. Diaphragm valves are also key here because they provide reliable control and prevent contamination. The system is designed to be sloped and fully drainable, making cleaning and sanitization much easier and more effective. Speaking of sanitization, whether chemical or thermal, it's essential for both production and distribution. Continuous turbulent flow circulation plays a big role in this, as it ensures thorough cleaning and prevents buildup. We also aim for the shortest possible length of pipework to minimize dead zones and make the system more hygienic. Isolating hot pipes from other lines is another critical aspect, reducing the risk of cross-contamination. Biocontamination control techniques, such as proper cleaning protocols and monitoring, help keep microbial growth in check. Circulation pumps are vital to maintaining a steady flow, which is necessary for both sanitization and consistent water quality. Finally, the requirements for water distribution pipework include designing systems that promote hygiene, efficiency, and ease of maintenance, ensuring the entire process remains safe and compliant. All these elements together support a robust and hygienic water system, aligning with our overall goal of maintaining high standards in production and distribution. To inhibit the growth of microorganisms, we can utilize several effective methods. One key approach is exposure to UV radiation, which damages their DNA and prevents reproduction. Maintaining the system temperature outside the microbial growth range is also crucial, specifically, keeping it below 25 degrees C or above 65 degrees C, where most microorganisms struggle to survive. Additionally, regular and routine sanitizing of the system is essential. This can be achieved through various means, such as using hot water above 70 degrees Celsius, superheated hot water or clean steam, or even chemical agents like ozone. These measures are vital for ensuring the system remains clean and safe, aligning with our overall goal of controlling microbial contamination and maintaining high standards of hygiene. For further support, please don't hesitate to reach out. We're here to help you succeed and ensure you have all the resources you need. If you have any questions or need additional assistance, just contact us using the information provided. Thank you so much for your attention and participation today. We appreciate your time and look forward to supporting you moving forward.